¿Qué pasa, Andrés? ¿Cómo has amanecido hoy?
Pues bastante bien. Lo que pasa es que os lo conté, ¿no? Que me tenía que, pase lo que pase, me iba a tener que despertar a las 8. Pues así ha sido.
Ha sucedido, ¿no?
Así ha sido. Me he tenido que quedar con Nicolás y luego, porque Sara llevaba a Inés y luego ya me he vuelto a meter en la cama un rato más.
Te has vuelto a meter en la crisálida.
Exacto. Pero bien, bien. ¿Qué tal vosotros?
Bueno, voy a poner esto a...
Entiendo que lo tengo ahí va bien, ¿no? Sí. Sí, ¿no? Un poco. Hola.
Uno subestima la capacidad. ¿La chagüita?
En- Pero ahora todo lo que digas se escucha en el mundo entero, ¿no?
Sí, pero si quieres lo...
No, no.
Si quieres te muteo.
Yo llevo así 2 semanas.
Por eso no quise venir.
Yo ya no contagio, esto se ha quedado conmigo.
Okay, so let's start. Thank you for coming. It's a pleasure for me to introduce a long-time friend from the university, Borja Anguiano, who did his PhD in the IAP in Boston, then moved to Australia, to Canberra, Sydney. Because in Canberra was when you were doing the PhD.
Yeah, I was visiting Canberra when I was doing the PhD on Sunday.
Okay, and then after that, Virginia,
Briefly in Texas, and now in...
brief stay in Austin, and now in the air. So Notre Dame is not Paris. And today he's going to talk us about anisotropies in the local velocity field, the galactic disk, and the dark matter density. So, whatever you want.
Thank you. Bueno, antes de irme a la lengua anglosajona, dar las gracias por la hospitalidad. Bueno, muchos sabéis que voy a venir a trabajar aquí. La verdad que con muchísimas ganas de convertirme en vuestro compañero en los próximos meses. Así que vamos a por todas. Okay, well, let's get started. Well, I want to thank first Gilden Chen and Steve Majewski. They are kind of contributions to the work I want to present today. Gilden is graduating this year at UVA. Wonderful study, brilliant career ahead. And Steve Majewski in the non presentation. Okay, this is happening. All right, yeah. Well, one of the quantities we measure, physicists is the mass of the objects, right? So this is a very old problem. Right? How massive is our galaxy, right? How massive are all the galaxies we see in the universe? How can we weigh something that you cannot put in a scale, right? That's the questions that Captain and Ord, more than a century ago, they were asking themselves, right? How we measure the mass of the sun? Well, I mean, if you know how the planets are orbiting, and you know your classic mechanics, you can infer the mass of the sun. So it's very similar exercise what we do here. How we are going to measure the mass of the Milky Way? Well, how the stars are moving. So, and this is what Captain and Ord they were doing a century ago, just using a handful of stars. They were able to measure the position of the stars. They were able to measure the proper motions, far away from the precision and accuracy we have today thanks to Gaia. And if they were lucky, they were access to a spectrograph, and they were measuring the radial velocity. They were combining parallaxes, proper motions, positions, and radial velocities, and they were able to obtain the 3D velocity, right? The velocity in the three components of the space. Using this information, okay, and using just what we call the Poisson equation, Jeans equation, they were able to infer the mass of the Milky Way. So when I'm looking at this is a century old. Well, first of all, we have a much larger sample that these people got. We have a much better precision and accuracy on the measurements, and we don't know what dark matter is. That's, we know that exists. It looks like particle physics will have the answer, hopefully. So I think it's very in to get better data and to repeat these kind of exercises to try to understand, especially the distribution of the dark matter, right? It's one of the big questions in physics. We don't know what it is. Okay, well, a little bit my motivation, as I commented already. We have Gaia, what a fantastic mission, right? And keeps giving, still the best has to come, right? We're going to have a good number of data released in the coming years. Okay, Gaia is giving you the parallaxes, Gaia is giving you the proper motions, the positions, you can get the kinematics of the stellar component of the galaxy. If you are able to measure the mass, the total mass, you are going to have the baryonic component, is the mass we see, right? You have the gas, you have the stars, okay, and then you are going to have the dark matter component that you can subtract once you know the total mass and you get the baryonic mass. We don't fully understand how this dark matter density distribution behaves in the Milky Way. It's clumpy, we don't know that. And thanks to the Gaia and the Apache, I will comment that, we can extend out larger volumes of study. We can use the pioneers in this kind of studies. They were just looking stars that they were just in front of us, like 100 parsecs away. Okay, and also we know we have different structure in the Milky Way. What we call it bulge, call it the thin disk, we call it the thick disk. All those are components that they are telling you the formation process of the galaxy, right? There are different epochs, and you can see how they have a different chemical evolution, and they have different kinematics. Can we make a selection of these different components? And of course, they have a different stellar age distribution. Can we have a clean selection without bias in your kinematics, it's very common to use the Tonre diagram to separate this. Now, thanks to services like Apache, Gaia, Rave, that they are giving you, now they come in width, they come in foremost, they are giving us also the abundances of the individual abundances, and you can make clean selections of the different structures because they have different chemical evolution. So that's a little bit my motivation. Also, to simplify your equations, you need to make assumptions. Some assumptions are quite difficult to get rid of, but you know you are already kind of like a bias in your study. For example, you have to assume that the galaxy is visualized, is in equilibrium, right? So the galaxy has not changed in time. You know this is not correct. Okay. Otherwise, you have the temporal components in the equations, and it gets really complicated. You will need a larger sample with extremely accurate stellar ages that maybe you can relax this assumption. Or you can go to simulations. What people have done to relax this is also go to simulations and try to see how the galaxy is evolving with time and see what happens with the total mass of the galaxy. Then you have to assume that it's axisymmetric. We know the galaxy is not axisymmetric, but also this one, you are not completely off if you assume that. I will show you later some results that how you can see that clearly that the galaxy is not in equilibrium, and this axisymmetric assumption, it just breaks. Also, you assume that, and this is, what I'm using here is the velocity tensor. When we talk about dispersion, okay, in 3 components, it's just the diagonal of the matrix. So you also need to use the non-diagonal components of the velocity tensor, and this is what reflects here. Again, this is talking about the symmetry. You will see the plots how this is going behaves asymmetry when I talk about the non-diagonal components. So also you are not completely off, but the idea was to use the data itself if I can relax these assumptions, and also like the bull motion is null. Okay, like the bull motion in the radial and in the vertical component is zero. Also, you are not completely off when you are assuming that. Okay, Gaia, knowing this introduction, I think everybody knows this wonderful mission, just parallaxes and proper motions with precisions of microarseconds. Okay, it was a complete revolution, and the best has to come. So I'm going to use the astrometry solution from Gaia for this exercise, particularly Gaia DR3. I mentioned that it's just the volume. Okay, here you have a drawing of the Milky Way, how we think with the Milky Way looks like. Nobody knows how many spiral arms has the Milky Way, but this is a good vision of how the Milky Way probably looks like. You know there is a bar, but what I want to emphasize here is the volume you are covering when you are using the new data that we have in hand, right? Here you have also break it in different spatial components, and it gives you an idea. This is just parallaxes plus priors, right? But it's giving you an idea the kind of the volume we are covering when you are playing with Gaia data. And of course, you have the Magallanes clouds appearing here. You have the core of Sagittarius. This is a dwarf galaxy just being disrupted by the Milky Way potential. The other survey I'm going to use is Apache. Apache is a finished product. DR17 was released 2 years ago, and Apache works in the H band. It's an infrared spectrograph, high resolution. It has been getting nearly 1 million of targets. We have a multi-epoch radial velocity, so you can also do binary studies, which is great. And also we were able to measure 20 elemental abundances. And this is one of the greatest things, and that's why I'm bringing Apache to this kind of study, because I mentioned early on that we have different structure in the Milky Way. So I want to use these elemental abundances to separate them, because they have been going through different chemical evolution processes. So wonderful survey. Everything is out. This is the fingerprint of the survey. So the red one is the south. It started in the north. Started in the Apache Point Observatory, and years later, we also started in the DuPont telescope in Las Campanas. You can see clearly, for example, here, this is the test, continuous viewing zones. There is some Kepler fields there, and also there is like the BALS program, the HALO program, and the disk. One of the greatest things to work in the infrared is that you can just you are less affected by the dust, and that's why one of the things that Apache, well, first of all, the volume you can cover is much larger, and also you can study. You don't need to avoid the galactic plane that most of the optical surveys they have, because yes, reddening just it gets a real mess. This is the volume of the study that when you use Apache data, you can see the fingerprints of the survey, right? No, it's not as continuous as Gaia, that is mapping systematically the sky. And also, we call it Apache as a Milky Way survey, but also we are getting very interesting local group targets. For example, of course, the Magallanes clouds. We have Fornax. There is also a few more dwarf spiral galaxies that we targeted, and also there is a program getting stars in Andromeda, and also the global clusters in M33. So I like to mention that Apache is not only a galactic survey, also a local group survey. Okay, well, so those are my tools that I'm going to use for this study. Well, we often think that the galaxy is quiet, right? That everything looks in equilibrium. And we know for a long time ago that this is not true, that the Milky Way is in disequilibrium, but not as clear as we see it now using Gaia data. This is the beautiful work from Teresa and Toja, where they discovered the phase spiral, right? This is just the vertical component of the velocity with respect to the vertical height, color coded by the azimuthal, by the rotational velocity, and you see that the disk is being perturbed. Very likely this is caused by the Sagittarius being accreted, and also probably the Magallanes clouds they have also part of the responsibility why the disk is being perturbed. This is the same study. This is just focused on the solar cycle. And this is the same study, just for a larger galactocentric radius. And you see that the phase spiral is not just a very local phenomenon. You see it in the entire disk. So clear evidence that the Milky Way is not in equilibrium. Okay. Further, this is a study we did trying to understand the galactic world. Okay, so here I'm representing the individual velocity components. Here is just the vertical one. I have a laser, I don't need to go there. And here is the angular momentum in the vertical component. The angular momentum in the vertical component is just it's the product between the galactocentric radius and the rotational velocity. So by that, when you are looking at this region, you are looking at the inner part of the galaxy, and when you are looking here, you are looking at the outer part. So first of all, you see that there are ripples happening here. This is the same plot, but now using the radial velocity, the radial component of the velocity. Okay, and you see clearly. Okay, so Gaia is giving you such a precision in your velocities that you start to see all this structure happening here. Okay, here I break it in what we call it the thin disk and the thick disk. That was chemically selected. I will get back to this, but you can see that these ripples that are happening in the disk are a phenomenon that is more present in the thin disk than in the thick disk. The thick disk is dominated by intermediate all stars. Okay? It's a fossil record of the pristine galaxy, while the thin disk is still forming stars. It's more so our goal was not to identify all these ripples happening in the galactic disk. We wanted to see what happens with the warp. Okay, you see how the velocity increases when you are moving outside, and then there is like a decrease here. So we didn't expect that. So we found that this is caused by the galactic warp. So we published this a couple of years ago. To keep going with this disequilibrium phenomena, here I'm representing the velocity dispersion as a function of the vertical height. This is a key plot for what I'm trying to do. So what is going to give me a total mass I measure in the Milky Way is just coming from the dispersion. Okay, and you see immediately. First of all, I break it in different galactocentric radius. This is the inner galaxy, and this is the outer galaxy. Okay, so first of all, you see that the velocity dispersion behaves differently depending when you are looking at. Okay, so there is a lot of phenomena happening here. And do you remember that one of the things that we have to assume is that if you are looking at the North Galactic Pole or the South Galactic Pole, you are going to assume that it behaves asymmetric. So you can see that this is somehow, you are not completely off, but the data is telling you that you have to be careful with this assumption. I will get back to this. So also you see these ripples happening that also in the velocity dispersion space, not only in the bulk velocity. Okay, so this is very interesting because now what I will use this velocity dispersion that I measure in different galactocentric radius to measure the total mass density. Okay, we don't need to focus just in the solar cycle. That is where traditionally we have been looking at. To keep feeding the horse, you have here the galactic warp clearly appearing here. Now the galactic warp very likely is also a gravitational perturbation from accretion events shaping the galaxy and also affected by Sagittarius and also the Magallanes clouds. Okay? So this is a beautiful work that they did with Cephis. Cephis can give you extremely precise distances, and so you can really see the warp phenomena just by plotting the stars in the space. Okay, well, so there is a lot of evidence that this assumption that the galaxy is in equilibrium is just breaking down, okay, which compromise these kind of studies. Other thing I want to take into account is the structure of the Milky Way. Structure of the Milky Way is telling you that you have different processes in the formation of the galaxy. Okay, well, on the 80s, very famous work from Gilmore and Reed. They were just counting stars. Okay, I'm going to the Smith telescope inside the Spring Observatory. I'm going to use all these photographic plates, and I'm going to start to count the stars. I'm going to work in the infrared, and I'm going to start to count the stars looking towards the South Galactic Pole in this case. And they found that, well, I need two exponentials. I cannot fit the number of stars per vertical height just using one exponential. And then they call it the thin disk and the thick disk. I think there is a lot of debate here. There are people who say that there is no thin disk and there is no thin disk. Definitely what we have is that there are different chemical abundancy strengths and different evolution time scales. Okay, so one of the things I want to take into account for this kind of study is also what happens if I separate chemically what we call it the high alpha sequence that is related with what we call it the thick disk and the low alpha sequence that is the thin disk. Other thing that is giving me these apogee abundances is that I can remove most of the halo stars. Previous studies using this, they didn't make any selection in abundances. So if you are bringing halo stars, and you are going to bring halo stars if you just select them in a volume, because we have halo stars just in the solar neighborhood, your dispersion is going to go up, and you may be missing your measurement of the total mass. So I want to remove the halo objects from this area, which is great. Surprise. Okay. When you make this chemical selection, you see that the different components, they overlap kinematically. Also, traditionally, we have been using the kinematics to select the different components. If you do that, you are going to bias your sample. Okay? If you try to select high alpha sequence or low alpha sequence or halo stars here pure kinematically, I mean, you can do it. Of course, we have been doing it, but you are going to bias your sample. So if you are trying to make a selection, for example, the Tonre diagrams is very common. That is just using the different components of the velocity to select different components. Then if you get back to do a clean kinematical sample, you have to understand that you already bias your sample. So here you have in blue the halo for the three components, the radial, the azimuth, and the vertical one. Then you have the low alpha sequence in black, and in red you have the thick disk. Okay, so we need to be careful. This is one of the things I like to combine the abundances with the kinematics, to be careful not to bias your sample a priori when you are trying just to do a pure kinematical study. Okay. This is also, I went a bit further with this. So one of the, okay, so if we have different components, you want to normalize that, okay? So you want to see the local, call it thick to thin this density normalization. So usually we have been doing that traditionally using stellar counts. So here I did it just using the kinematics. So I created a data-driven model using the different components because I select the thing that this and halo chemically. Then I was asking myself, okay, how many stars? What is the normalization that I need from the chemically selected different substratus from Apache to match the stars that I see in Gaia? In Gaia, I have, because I was using the subsample that has radial velocities, here I have like a 7 million stars. In Apache, I have 500,000. So I was using this 500,000 with exquisite individual abundances to try to understand what is the normalization of a 7 million stars from Gaia. So this is what I did in exercise, and I got a good agreement with previous studies using star counts. So, but a completely different approach. So that was fun to do this exercise. Let me get back to the velocity dispersion with respect to vertical height, because as I commented before, this is what is going to give you the total mass of the galaxy. But now, what I'm doing here is to break it in the chemically selected thin, thick, and halo. So you have, for the halo, if you see the different plots, in the green ones, you are going to see that they are the same. So we are not breaking, for the halo, we are not breaking in different galactocentric radius because we were running out of stars. There were not many halo stars, so we couldn't just beat the data because we were running, I mean, we didn't have stars, so we couldn't break it in different galactocentric radius. But I don't care here because what I want is to remove all the halo. Okay, so in the background you have Gaia. For example, do you see this abrupt here in the radial component in the inner part? This is very likely the bar. This is very likely the galactic bar, creating this deep sharp drop in velocity dispersion. So this, then you have another non-static component, the galactic bar, messing with your disk, right? It's a complex system, no doubts. So what you can see here is that it's also very interesting to see that the velocity dispersion for the thick disk is quite constant. Okay, you see the increase of the velocity dispersion for the thin disk with respect to vertical height, but also for the red points, that is the galactic thick disk, you see that it's quite constant. So you can see clearly that you are seeing different processes in the formation of the Milky Way. So this is the idea here. The idea is to use the different components, use the velocity dispersion I measured here, the different components separated chemically to try to get the total mass. How am I going to do? Okay, here is the outer part. So so see how the shape of the velocity dispersion with respect to vertical height completely changed when you are looking at different regions of the galaxy. This is the outer part. Okay. Also, you see how look how you still have a good number in the outer region. You still have a good number of stars. This is being okay in every point. I think there is a total of 200 stars. So you see how you are running out of the stars in the thick disk is because the scale height of the thick disk is smaller than the scale height of the scale length of the thin disk. So you really see that in the data. You are running out of stars in the chemically selected one when you are looking at the outer parts. Okay, well, so I have the data. Let's look a little bit at the theory. So this is just the Poisson equation. This is the origin of how you are going to use. If you are assuming that you are in a flat rotation curve, which is not completely wrong, okay, you can simplify this equation. So you have here the vertical force, and you have the gravitational constant here, and now if you break it, you start to get quantities that you can measure. like the scale height, the vertical component of the velocity dispersion, okay, the non-diagonal velocity dispersion. So those are quantities you can measure. So if you can measure this, then you can plug it in your equation, you can get the vertical force, and then you can get the total surface density. So that's the goal. This is a work from Moni Biden and also Borja and Remain. They were using a similar approach. So this is the vertical component, the velocity dispersion in the three components with respect to the vertical height. Traditionally, and I'm going to do the same here, but I wanted to go further, but I will explain why also I'm using linear fits. Okay, it looks like if you are able to fit your data with just a linear fit, you still, okay, this is what you are going to plug in your equations. Okay, you are going to, from what the slope you are getting here is what is going to give you this derivative. So this is using a Sloan data. Okay, this data was pre-Gaia. Okay, you see that in the error bars. Okay, I will show you in my results how this is getting. I mean, you have to be careful when you are trying to use a linear fit. My original idea, and it turns out that it's more difficult than I thought, it was to use the data itself. I don't want to fit anything here. I want to use the data itself and plug it into the equation. We were trying to do that, but we ended up that our interpolations, they were just messing around, and we didn't get meaningful results. This is our data. Okay. First, I'm going to show the data for the low alpha sequence that we call it the thin disk. It's breaking in different galactocentric radius. So here we're in the inner part. We are moving outside of the galaxy. So what we have here is the vertical component of the velocity dispersion, and here we have the non-diagonal one. Okay, that is what you are going to use to plug it in your equation. So you see the linear fit, okay, is giving you a reasonable good behavior of what you see from the data. Look, when we are getting closer to the solar cycle, you start to see all these ripples again. Okay, still, I mean, with the linear fit, it still keeps the general trend, but you are going to miss all this. And that will be very interesting, because if you are able to get these different ripples that we see in the velocity dispersion, to try to measure total mass, you may be able to see the clumpiness of the dark matter distribution. That was my original idea, but now it's more difficult. But I would like to keep thinking and try to dig more in this direction. But a linear fit is giving you a general good trend of what you see. Okay, and here I'm moving now to the thick disk, the inner region and the outer region, and you see also that we are using a linear fit here. So this is what you are going to use. I mean, the slope of this fit is what is going to give you the derivatives that you use in the Higgs equation. Okay, so this is how we have been creating our data set. Other thing we measure is what we call the scale length for the velocity dispersion. Okay, so we were using here the non-diagonal component of the velocity tensor with respect now to the Galactocentric radius. This big paragraph is just to tell you that we were getting reasonable values with respect to previous people who has been using a similar approach. And also we found that there is no significant difference for the dispersion in scale length for the chemically differentiated thin and thick disk. Okay, so now we have all the components that we want to be able to measure the total mass. It's a good practice to do sanity checks. Okay, so when you are trying to do an exercise, I mean, very likely other people have been trying to do it before, even if you have great data. So it's good to also to see if you are able to reproduce what previous people have done before. This is how physics works, right? So we were trying to do that here. Okay, let's see if we are able to reproduce what other people have done before trying to do that. Okay, so this is just focused on our thick disk population, and this is just for the solar cycle. Our results are the set region here in blue. The red line here is what we call it the standard halo model. It's just following the Navarro Frank and White profile. Okay, And this is the standard halo model that we use to try to understand how the baryonic plus the dark matter behaves with respect to the vertical plane. So in green is the from Bovian Tremaine and also the one from Hagen and Helbing. So we were able to reproduce what people have done for the solar cycle. You see here, traditionally, people have not been trying to understand what's happening. So one of the things is like they have been trying to avoid the young galactic disk. That is what we call it the thin disk, because they know it's not dynamically in equilibrium. So if you are not dynamically in equilibrium, your Lewis equation is going to break down. So traditionally, what people have been doing is to select the stars with a vertical height higher than 1 kiloparsec. Okay, so that's why you have this route here. Now in our study, we're going to start to see what's happening here, and this is very, very interesting. But anyway, so that was a sanity check, and we found that, well, we are able to reproduce what people have done before. I mean, we are doing something right, or we are doing it wrong in the same way that they were doing it. And this is one of the main results of this study. Okay, well, now here you have the total surface density, break it in the high alpha component and the low alpha component, in the thin and the thick disk with respect to the vertical. You have, I'm bringing here the standard halo model and also bringing here how the baryonic matter behaves with respect to the vertical. Okay? This is the inner region, this is the outer region, and I will get back later to the most outer part. So one of the first puzzle things that you see here, well, so you have selected chemically, just chemically, two different components, two different structures of the Milky Way. Is what we call it the thin and the thick disk. You study the kinematics of these components, and you bring your gene equations to measure the total mass. And you get completely different results. Gravity is gravity. Why you select a component chemically? You apply the same theoretical framework, and you get completely different results. What is happening there? Okay, this is what my second part of the talk is trying to understand why these discrepancies are. Is our theoretical framework too simple? The Milky Way, this is way more complex than we think, that you cannot just approach this simple analytical expression to try to understand something that is much more complex than we thought before. And it's also interesting how the total mass and the K4 change, right? Okay, so you see that there are some regions where the prediction from the standard halo model, it looks like agree with the data, but there are some other regions that the discrepancies are getting larger. Also, we are looking close to the galactic plane, where traditionally people have been avoiding this, just selecting 1 kiloparsec in the vertical height. It's also very interesting how the thick disk, it never goes down close to the plane component. I will get back to this. So that was puzzling. We didn't expect that. It's like why you select chemically as a population and you get different answers when you are trying to measure the total mass of the galaxy. Right? Okay, so let's try to break down the problem. This is the same result. It's just instead of plotting the total mass with respect to vertical height, now I plot it with respect to galactocentric radius, and I break it in vertical height. So you can see clearly when you are close to the plane, the discrepancies between the thin and thick disks are much larger, and also with respect to the standard halo model. You see, you are around 1 kiloparsec, the agreement with respect to the agreement between the thin and the thick disk and the standard halo model, it looks much better. And then when you are going up, well, you don't have thin disks anymore, so you are dominated by the thick disk, but it looks like the standard halo model and overestimate the prediction of the total mass that we observe. All right, let's try to understand what is happening here. Okay, well, what are the sources of discrepancy? Well, is the density profile. You have to assume you are one of the terms that you need for the Lewis equation is what is the total number of stars you have, not the total number of stars you have. What is the density load that these stars take? So we were using the two exponential ones, okay, and the most common values that you find in the literature for the vertical height, that is 0.3 kiloparsecs for the thin disk and 0.9 kiloparsecs for the thick disk. The key thing here is that these numbers, they make sense depending when you are looking at the galaxy. So while these values are very values if you are in the solar cycle, when you are moving away from the solar cycle, these values may mean no value. And that could be one of the sources of the discrepancies. When alphas are not happy with exponential density laws, they have what we call it the squared hyperbolic secant that is just observationally motivated. Okay, there is a discontinuity when you are close to the galactic plane when you are using the double exponential. So the hyperbolic secant breaks this discontinuity. All right, so let's use this as our density profile, and this is the result we found. Things get even more how to say, a little bit more off when we were using a different density profile that is not the traditional exponential density law that is more common use. Okay, so I mean, it's a complex system. As I said, probably has to do more that you are assuming that depending when you are looking at, you are assuming these values, and these values may be different if you are looking at the inner or the outer region of the galaxy. Other thing that we use is the velocity dispersion profile. I mentioned I was using a linear fit. Well, let's try to use other different fits. Let's try to do a quadratic fitting. Let's try to use a hyperbolic tangent fit. Okay, so you see that you are more or less able to get the general trend that you see in the velocity dispersion with respect to the vertical height. Okay, what happens if we use these fits and the result of these fits in our Jeans equation? So we get something like this. Well, still, you are not able to get the same result for the total mass, total density with respect to the vertical height for the thin and the thick disks. And now you are off of the prediction for the standard halo model. Okay, so using different fitting processor in the velocity dispersion also looks like it's not solving completely the problem you have here. What else? Well, Quigen and Gilmore in the 80s, they also developed what we call it the integral approach. We have been using the differential approach with the equations. So they developed what we call it the integral approach that is using the tilde term of the dispersion. So we were trying to, okay, let's bring this approach and let's see if we can get something that is more in agreement between our chemically selected populations and the predictions from the standard Halo model. So here we were able to get a good fit the data. Okay, so the theoretical framework using the integral approach was able to give us a reasonable good fit for what we see in the data. But this is very interesting. Okay, so when we were getting the density of the dark matter, we found the opposite. Okay, so what we got for the thick disk was in better agreement that we were getting for the thin disk. Okay, but still the numbers that were of what is commonly affected about the total density of the dark matter. Okay, so it was very interesting. So it's like when you are using this differential approach or the integral approach, it's not only not solving the problem, it's that you are getting the opposite results for the chemically selected populations. So that was even more puzzling about what we were observing here. Remember that we have assumed that the galaxy is in equilibrium and there is no time dependence. Okay, well, we know this is not correct. So maybe this analytical approach is too simple. Okay, well, it's a great step to start to try to dig in this problem, but you may need to go to cosmological simulations to try to understand much better how the non-equilibrium and the time dependency is affecting all these measurements. Also, I mentioned we have a galactic bar. The galactic bar is a time-dependent phenomenon, and we know it's affecting, okay, all the kinematics that we observe in the galactic dips. Okay, well, so maybe what we observe here is just that we need to treat this problem with the complexity that deserves. Okay, so maybe this analytical approach are just a good toy to start, but we may need much more complex treatment for this problem. Other thing that it was in years ago, I think people has abandoned a little bit this idea, is the existence of the dark disk. Okay, so embodied simulations, okay, this a dark matter disk-like that correlates with the galaxy. So that was observed in embodied simulations. Okay, so I was thinking, well, why when I'm looking at the inner region, okay, I see a larger amount of mass that is predicted. Okay, well, is this and seeing the effect of what people in embodied simulations detect, and they call it the dark disk. So we bring it up in the paper as a potential explanation why when we are looking at close to the galactic plane, okay, we observe that the total mass is much larger than the predicted one. Okay, well, so we leave it there as a potential explanation. There is some results from people using Gaia also suggesting that maybe there is a dark disk in our galaxy. So, still we don't solve the problem why the thin and the thick disk is giving us different results, but we wanted to bring this as a potential explanation. So I'm moving here to my final points. So we wanted to attack this study using just the exquisite astrometry from Gaia, just taking advantage of the Apache abundances to make a selection chemically in different components, different structure of the Milky Way. We found on the way significant ripples on the 3 dimensions of the velocity dispersion, and also just to remark again, we found important discrepancies between the chemically selected thin and thick disk total density that we measure, and also important discrepancies with respect to the standard halo model when we were looking at different regions using the Galactocentric radius. And I think I'm going to stop here. I'm going to give you thanks for your attention.
Thank you very much, Borja. And now questions? Elena.
Hi, Borja. Thanks a lot for the talk. I have a very basic question. So why would you expect the stellar mass density of the 2 components to be the same if you're tracing different parts of the galaxy? I mean, so if I understand correctly, you measure the kinematics, and from the kinematics you derive the total mass.
Yes.
But it's the total mass of those components for which you measure the kinematics. So why should they be the same?
Well, you use a double exponential, and what you have there is the scale height and the scale length. Okay, and those numbers are different for what we call it the thin disk and the thick disk. Okay, so it's a density law, but if you will be using
maybe my question is, when you plot the radial profile of the stellar density, is the total stellar density or the stellar density of those stars for which you measure the kinematics?
So because I break it into the thin and the thick disk, okay, you use the density law for the different components.
Yeah.
Okay, so this is what it's telling you here. You cannot just do a single exponential.
Okay, so then you combine them with the weights and to get the total mass.
Yes.
I see. Okay.
Yeah.
Okay.
More questions? A ver.
Let's see if I can explain the question. So you have focused on the difference between the thin and the thick disk in the stellar mass, but then at higher altitudes of the disk, at 3 kiloparsecs, you found that is what the mass was less than expected, kind of. But you didn't explain. Well, you didn't say anything about that, so I'm curious about if you explained something.
Well, I found important discrepancies with respect to the standard halo model. Not only a 3 kiloparsec, also a different galactocentric radius. So all what I found is that when you are a 3 kiloparsecs excursion from the galactic plane, the prediction from the standard halo model is giving you a larger amount of mass than the one you observe from the data. That's what I found. The reason why, no.
Okay. But you didn't explore it, or what are your thoughts about that? I don't know.
My thoughts about that is that I think we need to be careful with this analytical approach. I think the Galactic disk is such a complex system that maybe this analytical approach of the K-force is just breaking down. It's not breaking down. It's just that you may need to go to embodied simulations where they're taking account all the non-equilibrium and the time dependencies to try to get this size right. I mean, it's just I cannot tell you here. It's like clearly from my results there is much less dark matter than we thought. I have to be careful with that. I cannot say that even if I see it in my data, because probably it's this analytical approach what is breaking down.
Ricardo?
Yeah, I have a very basic question. So, are these ripples that you see in the velocity dispersion of the stars related with the correlation patterns that are seen in simulations like Omega or Milky Way?
That would have a great exercise to do. That would be that. I mean, yeah, that's okay. We try to do it. We try to see very simple. When we found all these ripples, if you see here, I didn't mention that. Okay, but here you have the spiral arms.
Mm-hmm.
So we try just to let's plot where the spiral arms are living and see if they are related. We did that very simple. No, we didn't do any statistical analysis. So we tried to see, and then you can say like, well, this big ripple here, it looks like just between two spiral arms. I mean, but what you're saying is a great exercise, try to explore, try to bring the simulations to the rotation, try to see where the spiral arms, and try to see what the data is telling us. To see what is. It's very in right now. There's a lot of people trying to understand these ripples. It's in galactic dynamics. It's a big topic right now.
So I guess if this is due to some vertical perturbation and things like this, so the rotational potential changes, so it becomes more complex. Therefore, your analysis of the mass density and stuff like that.
Yeah, a potential that is time dependent also, but you have to go to simulations.
Mm-hmm.
Yeah.
I think Andres has a question.
Oh, yes, I have a question. Very nice talk, Borja. I like it very much. So as you mentioned in your talk, the Milky Way is not exactly in equilibrium, right? So it's subject to perturbations from other systems. Particularly important is the perturbation coming from the LMC and the SMC.
Yes.
It was shown in 2019 by Garavito et al. That basically the closed passage of the Magellanic system is causing a dark matter wake in the stellar halo of the Milky Way. So I was wondering whether this perturbation would be in the right direction to explain the let's say the weird fitting that you show, or it's going in the opposite direction. Like, could this explain some of the inconsistencies that you were explaining in the conclusion of your talk?
Well, Andres, this is work to do, I guess. Clearly, what we see from the data is that this is being perturbed. Okay. You also have Sagittarius, and you have also you have all the merger activity in the past that we observe there is a myriad of stellar strings in the galactic halo. Mm-hmm. So you have all this activity. Then you have the Magallanes clouds, okay, that very likely they are in first infall. You have the Sagittarius stream being disrupted. That we have this beautiful work from Tomás Ruiz Lara, no? That you see the star formation peaks when the Sagittarius stream was getting closer to the galactic disk, right? Well, that's a study to do. I don't think we fully understand. It's like, okay, clearly this ripple that we see in the velocity dispersion is because the Magallanes clouds was closer, and this one is related with the Sagittarius stream. I don't think nobody knows that. I mean, I think that would be a great also exercise to explore, and complex. extremely complex, I would say, Andres.
Yes. So the thing is that for small systems, I would expect them to be causing ripples, but the effect that I understand the Magellanic system is provoking in the Milky Way is something like large scale, like the entire galaxy is moving, right? And so that's why I don't know if this would, in principle, affect more the stellar halo or the disk or whatever. If that could explain the difference in densities that you observe. About the ripples, yeah, that's a completely different animal. Is very complicated.
But also very likely, those are maybe internal phenomena in the disk itself. Gaia molecular clouds, spiral arms, transient of spiral arms, star formation activity. Probably when you are close to the disk, maybe secular processes are dominating. And when you are moving away from the disk is when your satellites, they may start to play a role. I would say.
Yep. Thanks.
I was wondering why we didn't see any age estimations here, because you have, for example, Apogee in those plots, or even with Gaia, you can make some age estimations, and that can be helpful if you want to track in the past all these things. So why didn't see any age here in this?
How do you measure the age of a star?
Huh?
How do you measure the age of a star?
For example, from the point, you can use color magnitude diagrams, or there are many works that have been made estimates about the age of the apogee stars.
Okay, you go to the Hertzsprung-Russell diagram to measure ages. You need a theoretical framework. You need isochrones.
Yes.
Can you use all the stellar populations that you observe there to get stellar ages? What happens with the isochrones in the mind sequencing?
Oh yes, there are a lot of degeneration age in that point, and if
you have from 2 gigayears to 12 gigayears for a range of metallicity, they are all together. So if you try to measure ages there, you have 10 gigayears error bars. Turn off and subgiants using isochrones can give you ages. Okay, still 2 gigayears and 30 days. Asterosismology can give you ages. The samples that we have where you can trust the ages is very small. Okay, so it will be interesting to bring the ages to do the same exercise breaking in different ages. That will be interesting. Problem is that the number of stars that you can trust the age is still very low. That's why I didn't bring the ages here.
But for example, in the case of Apogee, you have a few stars and they are tracing those ripples. And for example, I'm telling this because I saw many works which use Apogee to track trace different population in a
very global, like for example, really inner part and outer part.
Okay.
Like okay, I'm going to break whatever is lower in galactocentric radius than 8 kiloparsecs and larger than 8 kiloparsecs.
Yeah.
And then you see kind of like a gradient. Okay, look, this is dominated by young population, this is dominated by. But if you really want to bring individual stellar ages, you have to be careful. I mean, it's the holy grail, right? A little bit in galactic archaeology. We do galactic archaeology, but we are not able to measure good stellar ages. So it's. But yeah, stellar ages is just. That's why asterosismology is so strong. It's like we can measure the mass of a star very precisely just by oscillation. And then the density, and you get the mass. And then it's like you bring your isochrones, such a precise masses, I can give you the ages. That's why asterosismology was very big. Well, Kepler test is giving you that, but the number of stars you have is still very small.
Yes.
And this.
Thank you.
This future.
I was wondering, how would the dark disk cause this discrepancy between the thin and thick disk? Like, what would be the mechanism?
Well, because the standard halo model is not taking that into account. And you see that the total mass I measure in close to the galactic plane is much larger. So when I say, oh well, there is a larger amount of mass there than the model that is not taking into account the dark disk predicts. And some people has published papers that they see this dark disk from the M-body simulations. So when you have like within you have a satellite accretion at given inclination, it forms kind of like a co-rotating dark matter disk. And then it's like, well, do I see that in my data?
So it's a difference in the mass measured at different scale heights.
So
There's a different distance from the disk, from the plane.
let me see here. So yeah, when I was looking close to the galactic plane, so the red line is the standard halo model.
Mhm.
So we found that the amount of total mass it's much larger than the predicted one. You see that clearly here. This is for a vertical height of 0.3 kiloparsecs. So, but again, you still have a discrepancy between the different populations. Why is that? It's like maybe you have to be careful with your analytical approach and make strong conclusions. So that was one of the. We were trying to explain in the paper. We were trying to explain why we find this discrepancy. So I also wanted to bring this. Jin and Steve, that they are the co-authors in the paper, they were skeptical. I said like, well, I want to bring it because it's kind of like because it's very interesting. Nobody has been exploring close to the galactic plane. They know that, okay, first of all, you have a discontinuity if you use an exponential when you are at zero, right? So a lot of people has been just looking at whatever is larger than 1 kiloparsec. Also makes sense because you are trying to measure the dark matter. So the amount of dark matter here is much larger than here. That is the baryonic one that is driving it, right? So that's why people were looking more in this region. But
The standard halo model is derived from simulations that still ignore the hydrodynamics. So it's like just dark matter interaction, not all the complexity of the disk. So I think it's expected that it doesn't work in the disk part of the galaxy. So yeah, I was just wondering, like, how would the dark disk create this discrepancy in the chemically selected populations?
Okay. One last question, and then we finish. Is there an active discussion about alternative to dark matter? Is that on the table, or is?
You have more.
Yeah, but my question is more that is there an active discussion about that? Is a possibility that the people in the community consider because you cannot explain this part?
Let's try to bring an alternative theory that is not that matter to see if we can explain what we see observed here. This is what you're trying to.
Yeah, I mean, in the community, is there an active discussion about, well, we cannot explain this, we should check MON, or is more like, no, this is too complex. Dark matter is still the first, second, and third option. So let's explore our analysis method and the dark disk and all these effects. And the other thing is like probably is.
Well, I'm aware that there are people working on MON. It looks like MON is the bank, not like well, there were some papers recently saying like MON can explain that. But I'm not aware that there are people trying to understand the surface mass density using MON. I'm not aware of that. I'm not aware that there are people looking at that.
And the difference, like MON would be able to explain the lower acceleration regime. So in the central part of the galaxy, MON would point to not dark matter. So you would expect the gravity of the stars was the main thing.
Well, but at 0.5 kiloparsecs, the standard halo model is already over the stellar potential. So either in the inner part, you should see something. Okay, thank you very much. You are dismissed.
Esto estaba buscando yo.
Adiós.
¿Estás vivo?
Sí.
Oye, Andrés, ¿te vienes a comer luego?
Sí, 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 más o menos.
Cuento contigo, ¿no? Vale.
No sé dónde teníais pensado reservar.
Yo tampoco. Voy a llamar al portal ahora, a ver si me cogen.
Vale, vale. Bueno, cualquier cosa me lo decís por WhatsApp, ¿vale? Pero
Sí,
yo...
lo pongo por el chat.
Venga, muy bien.
Venga, hasta luego.
Ahora, chao.
Pero bueno,